Hi all. I want to discuss another reaction that goes through the enolate. It's called the Claisen condensation. It's a different reaction than the aldol, but honestly, if you know the aldol very well, then you can consider the Claisen, or I like to consider the Claisen, as an aldol reaction using esters instead of aldehydes and ketones. You'll recognize some familiar elements in the Claisen condensation that you remember from the aldol condensation. For instance, we have alpha protons that are acidic. We have a base. And yes, we're going to form the enolate, and it's going to attack another one of itself, just like we saw with the first type of aldols that we studied. But before we do the mechanism, there's something different about this reaction, and that's because when we attack the ester, you know from your carboxylic acid derivative unit that there's a leaving group, and that's going to affect the final product. It's not going to look like an aldol product. I want to write down 3 important points that should be in your head if you think you're doing a Claisen condensation. Alright, first, if you think you're doing a Claisen condensation, the base used to form the enolate has to match the alkoxy group of the ester. If we take a look at our first reaction here, the base that we're using is methoxide, OCH3-, and that has to match the leaving group of the ester, or the alkoxy group. So this is OCH3. You know, when this leaves under basic conditions, it leaves as OCH3-, the minus on the oxygen, same as the base. That's because, true, the base will deprotonate the alpha carbon, but also there might be transesterification. But you notice that if this OCH3- attacks the carbonyl, ultimately kicking out this OCH3, you don't notice that. It's the same group. So even if there is exchange of the base with the alkoxy group, just like in transesterification, it doesn't matter. You still have the same ester. That's number 1. The base used has to match the alkoxy group. Number 2, the ester that becomes the enolate, and here we only have one ester, so this will become the enolate, some of it, right? Just like in the aldol reaction, some of it becomes the enolate. Well, anyway, that ester has to have at least 2 alpha hydrogens. If it only has 1, then the product that you make, the Claisen product, will actually reverse back to the starting ester. See? And we have that situation here, where we only have 1 alpha hydrogen. Well, we're not going to form the Claisen product, and we consider that no reaction. It will just go back to the starting ester. I'll explain all of these points as we get to them in the mechanism. The last one, number 3, after reaction 1, the product is an anion that needs to be protonated in reaction 2. So when you do the mechanism, reaction 1 will give you a product that's an anion. And that's why for Claisen condensation, you have to have a second step, which is protonation. Why don't we go ahead and do the mechanism for the first reaction, and we'll incorporate all of these 3 points so you realize why these are super important. Alright, I recopied that first reaction, and I'm not going to draw the product. Why don't we do the mechanism first, and then we'll figure out shortcuts to draw the product of a Claisen condensation. We do have this alpha carbon here, and I didn't mention it yet, but we do have the base that matches the alkoxy group, but also the solvent, right? You don't want to use water, because if you mix water with this base, you'll get some hydroxide, OH-. So you want to match the solvent also with the base. You want the solvent to be the protonated form of the base, or the, I don't know, you could think of this as the conjugate acid, or just the neutral solvent. Okay, just like an aldol, you're going to form the enolate. Do we remember the pKa of an ester? That's a good question actually. It's less acidic, so the pKa of an ester is 25. It's less acidic than a ketone or aldehyde, around 25. But we have some base, and we are going to make some of the enolate. And how do I want to draw this? I'll draw it like that. Make the double bond and kick up the pi bond to the O-. And everything will be at equilibrium. And we have this. I want my students to draw the oxygen anion form of the enolate. We have this leaving group, which we'll take care of in just a bit. So what I mentioned was we only form a little bit of this because look at your conjugate acid. Your conjugate acid is methanol, and that has a pKa of 15.5. So the left side has the weaker acid, but it doesn't matter. We just need a little bit of this, and then we need this unreacted so we can attack it. So just like we saw with aldol, you make the enolate and you attack another one of itself. And another one of itself looks like this. I'll put the dot. Okay, so we keep track. We'll keep track of the alpha carbon and the dot, because you know that's where the connection is going to be made. Hit the dot. Make the tetrahedral intermediate. Now, how do I want to draw this? Let me flip this and put the alkoxy group on the left. And then we made a connection to the dot. Okay, so this is looking a lot like an aldol product. You form the tetrahedral intermediate after you attack the carbonyl carbon. Okay, now instead of protonating like we do with an aldol, right, the aldol has aldehydes and ketones which don't have a leaving group. This one does have a leaving group. So look what happens. We form the carbonyl again. We still have the dot. We still have these 3 carbons, and I'll draw them here now. 1, 2, 3. We still have this alpha carbon that has these 2 carbons. And we created a leaving group. Now here's where that rule comes into play, where we need an alpha hydrogen that has at least an alpha carbon that has at least 2 hydrogens. We already stripped off 1 to make the enolate, that one there, but actually we need the second one right here to make the anion. Let me do that first, and then I'll explain what happens if we don't have that hydrogen. Very interesting. So it doesn't really matter which oxygen you make the minus, but it's most likely it's going to be this one that doesn't have any competing resonance. It's more stable to put it on the anion on that oxygen there. Honestly, I probably wouldn't take off any points if you put it here. But yeah, what we have is this, and that's the anion that I say occurs after the first reaction. Oops, you don't see that. Just be careful. Make sure everything's still there. There's your alpha. Okie dokie. So this is done after the first reaction. So this is your anionic Claisen condensation. The next thing is, why do we call this a condensation? Because we're not really making water, right? We're not doing a dehydration, but we are making a small molecule, in this case methanol. So there is literally condensation. You are forming methanol every time you kick out that leaving group. This has a very strong driving force because take a look at the pKa's. This deprotonation is the driving force to make the more stable anion, right? Equilibrium favors the weaker acid. So what we like to say is that deprotonation is the driving force for this reaction. It pushes the reaction forward. Deprotonation, or you could think of it as the motivation. Now, if we didn't have this hydrogen, let's say this was a methyl group, we wouldn't be able to form the anion. We wouldn't be able to isolate this because what would happen is that base would reattack the carbon, the dot, and it will reverse. And it will go back to what? It will go back to having two molecules, right? Remember entropy? It's more favorable to have two molecules than one, because one, your system becomes much more ordered. Two molecules has more freedom, degrees of freedom, more chaos. So entropy tells you that you're favoring actually the starting materials, particularly these two. So without this driving force, you are going to reverse. So you need this second hydrogen. The last step, and it's pretty short, right? Pretty short mechanism. You just have to keep track of this relatively large molecule where everything goes. We're going to protonate the alpha carbon, and we do that by reforming the carbonyl, taking that bond, and picking up that hydrogen. And yes, this now is your final product. This sort of confuses students a little bit because they know that this is the final product, and it looks like this. Okay, looks like this, and that's what they would draw up here, right? But the thing is, you see that product right here. It's just that you can't avoid having this base just sit there and not do anything. Either that base is going to strip off the second hydrogen, and if you don't have that second hydrogen, that base is going to attack here and reverse to make two molecules of the ester, which is entropically favorable. So that is the Claisen condensation. It's not a lot of steps. You just have to keep track, again, of what is attacking what. It still follows that the alpha attacks the dot, and that's the new bond. Okay. What do we get here? Remember how for the aldol condensation we said we got an alpha-beta unsaturated carbonyl? You know, that's one thing that I always want to check for before moving on to the next problem. Did I form the right class of molecules? This is called, what is this called? This is called a beta keto ester. Okay. You notice that when you have these two esters, one of them keeps its alkoxy group, the other one loses it. Okay. Did I count the number of steps? 1, 2, 3, 4, 5. It's the same number of steps as an aldol condensation. And the first two are definitely very similar. Make the enolate, and then attack another one of itself. So, let's go back to our original reaction, and can we shortcut this? Without drawing the mechanism, how do we draw the product fairly quickly? If you know you're doing a Claisen. You know you're doing a Claisen when you have an ester, and that's the only thing you have, and you have a base. You're going to make the enolate, and what's going to happen? You're going to attack another one of itself. So let me draw it up here actually. Okay, and just like I did with the aldol condensation, I labeled the alpha, that becomes the enolate, and then I'm going to put a dot on the carbon that it's going to attack. So you're making the connection between these two. Okay, right? Between the alpha and the dot. Now because we have an ester, that's the leaving group. So I'm going to remember that in my final product on the dot, we don't have this group. See, that's the huge difference between attacking an ester versus attacking a aldehyde or ketone. So take a look at how I'll draw this. I like to draw the attacker as is. Oh man. Oh no, I'm good. As is, with the alpha carbon ready to attack to the northeast. So 1, 2, 3, 1, 2, 3. And here's my alpha carbon. It's attacking to the northeast, so there's my dot. So that's the dot over here. You keep the carbonyl, okay, and you draw what's on the dot, except don't draw the leaving group. So 1, 2, 3, and that's your connection. And you can always double check. This is now a beta keto ester. Okay. Let me talk briefly about reaction number 2. You want to analyze this, and if you need to draw it, and actually I recommend it, if you think you're doing a Claisen, because you have an ester and base, okay, draw your alpha hydrogens. And I'm going to draw my one hydrogen here, and that alpha carbon only has one hydrogen. It doesn't follow this rule. And I already explained during the mechanism, if that hydrogen doesn't exist, this one right here, right? Let's say this was a methyl group, right? So that methyl group would be right here. Oh, yeah, perfect. That methyl group. Okay. So we remove the H to form the enolate. Now, if that was a methyl group, there's no driving force. There's no proton to remove to get to the more stable anion. And it's actually more likely that it's going to break up into its two pieces and reverse back. When you get to this point here, again, because the pKa is much higher, or relatively higher than the starting material, starting beta keto ester, then it's not going to reverse. It's not going to reverse, or it's not going to reverse in appreciable amounts. You could trap this and you could isolate it, and then go ahead and add your acid to make your final beta keto ester. Okay, so one more challenge. Reaction number 3. Will this give me a Claisen condensation product? So let's do our analysis. We have an alpha, and cool, we have 2 protons. Okay. Oh, I have a question mark here. If I want to do a Claisen, I gotta match, the base has to match the leaving group. So there are a couple ways you could draw this. You could draw it like this, O minus. Okay, and that's a good base, an oxide base. Or like in these cases, right, I pair it up with the counter ion. So you could do that, or you could write the salt. It doesn't really matter. When you throw this into a solution, liquid, alcohol, it's going to dissociate anyway, and you have the O minus to do the deprotonation. Now the solvent, remember what I said about the solvent? It's just the neutral form of the base. So we'll put here maybe and. Your solvent is going to be, it's a 2-propanol, or you could think of this as isopropanol. You're going to attack another one of itself, and if you need to, eventually you won't have to, but it's good practice, or it doesn't take up too much time to draw your second ester that you are going to attack. And again, you're going to kick out the leaving group. If you want to pause the video here, see if you could draw the product based on our shortcuts. Okay, let me draw the product in, let's see if this shows up in a different color. Let's do light blue. Oh boy. Oh boy. So I gotta turn this around. So I am going to draw the alkoxy part on the left. There's my alpha. And that alpha is connected to this isopropyl group. Okay. I have the right number of carbons. That is connected to the dot. The dot keeps its carbonyl. It keeps its the group on the left, but it loses its alkoxy group. That is your product.